Okay, now, so if you look at this ideal gas equation, what is going to be the value, the unit for N and T? Okay, N is going to be number of moles. Okay, so temperature must be in Kelvin. So therefore, the answer is D. Okay, so that one no problem. But if you look at the second question, okay, this one, okay, you need to be a bit careful. Okay, so I will copy this question. Okay, and I will use, okay, another one. Now, if you look over here, okay, they are, okay, if you look over here, they say that, okay, you have a sample of pure gas and they put it at temperature 300 Kelvin and the pressure was 16 kilopascal. So let's say you want to change it into Pascal also. Okay, I just change it over here. The gas is compressed until the volume occupied by the gas is half. So it means now the earlier volume is V. Okay. Now, after compression, the V now becomes half of the V. Okay. So if you're confused, okay, I will just change this. Yeah, just put half V. Okay, it will become half V. And then, okay, after the compression, the temperature of the gas is going to be, the temperature is going to be 375. Pressure was 40 kilopascal. So I just put over here. Now, my work over here is just to find out whether, do they satisfy ideal gas formula, PV equals to nRT. In this case, you're using the same gas. So it means the number of moles must be the same. If I can prove the number of moles is the same, it means that they are ideal. So you just use the formula PV equals to nRT for the first one, yeah? For the first one, so it's 16, 10 to the power of 3, the V, and then N, okay? So assume this N, okay, must be the same with the next one, yeah? So just put it as N1, okay? N1, that R, the temperature is going to be 300. Okay. After compression, okay, you have KPV. So this is 40 times 10 to the power of 3. And then the volume now is going to become, okay, the volume now is half V. And then let's say now is N2. Okay, but we know N1 and N2 should be the same. Yeah. So R, okay, and then we have, okay, 375. So if I just use these two equations, okay, equation 1 and equation 2, okay, if I further simplify, okay, this one, okay, if I put it over here, 16, okay, times 10 to the power of 3, V equals to N1 R 300. This one is divided by 2 is going to be 20 times 10 to the power of 3 V equals to N2 R 375. Okay. If I divide these two, 1 and 2, okay, the V will cancel off. Okay. The R will cancel off. Okay. I will have 16 divided by 20. 10 to the power of 3 also cancel. Equals to N1 divided by N2. 300, okay, divided by 375. Okay. What you do, you just find out what is N1 divided by N2. Okay. N1 divided by N2 is 16 divided by 20. You divide with 300 divided by 375, which is 16 divided by 20 times 375 divided by 300. You try to calculate this, okay? And you will get, okay, this one 4, 5, okay, this one is going to be 75. 75 times 4 is 300. 300 divided by 300 is 1. I managed to prove, okay, that Okay, my N1 divided by N2 is 1, which is N1 equals to N2. It means that I managed to prove that the number of moles is the same. If the number of moles is the same, it means that it is ideal. So coming back to the question, okay, here, okay, which statement is correct? Intermolecular forces are significant. No, it's non-ideal in that case. My answer must be it is behaving ideally. Okay. So if you look impossible, it's possible to calculate number of moles. It's impossible. We can only get the N1 equals to N2. You cannot calculate. Okay, so this one is also wrong. Okay, and then the pressure used are too high for ideal gas behavior. Okay, this one too high means it's indicating it's not ideal, but we have proved that it is ideal. Okay, my screen is dirty. Okay. Anyway, okay, let's actually look at question number 3. Okay, so chlorine and bromine has different volatility. Okay, so if you look at chlorine and bromine, Cl2, Br2, and I2, okay, CDI. So we know that okay, as they go down, they are generally getting bigger and bigger. And I told you, the bigger the molecule, they have more electrons. Okay, so more ID. So it means that okay, the boiling point as you go down the group, okay, the boiling point is going to increase. Okay. So if you want to say something is more volatile, it means we are looking into boiling point which is lower. So if you look over here, which one is going to be having the lower boiling point? Cl2 is the one that is going to be lower boiling point compared to the rest. So Cl2 is going to be the most volatile. Okay, why? Because okay, is ID is greater in bromine. Yes, ID is greater in bromine compared to chlorine. Okay, so this is going to be the answer. Okay, it's not the other way around. Okay, so we have to find out which has the lower boiling point. Okay, now for number 4, okay, this one not in your syllabus, okay, but they can ask you in different way because most of the time students see Si2, okay, Si join with O and Ola. Just straight away say Si is bonded to 2 oxygen atom. No, this is wrong. Okay, you can refer to my PowerPoint slide. Si is bonded to 4 oxygen atom. Always remember this. Okay, and okay, each oxygen atom is bonded to 2 Si. Okay, so this is going to be covalently bonded. Okay, so covalent, X is 4, this is 2, this is the answer is C. They have asked this, okay, a lot of students made mistake. I'm very sure that they can ask this, okay, but they can work around with the restriction of the syllabus. They didn't mention about this, but maybe they can give you a diagram and say that this is similar to diamond. They try to relate to your syllabus and then say how many atoms that silicon, how many atoms of oxygen is bonded to silicon. So you need to find from the diagram. They can still ask you from that. Okay, so please take note. What type of bonding never found in elements? Yeah, please remember elements can be maybe neon. Okay, it can be also P4. It can be also S8. Okay, all these are okay elements also. So if you look at it, okay, P4, okay, they have covalent bonding. Okay, elements can have covalent bonding. They cannot have ionic. Okay, ionic must be bonding between negative and positive ion. Okay, so cannot. Metallic bonding, yes. Okay, metal, okay, let's say copper, yeah, they are going to be element also. And then van der Waals forces is divided into 3. Okay, hydrogen bonding, ID, and PD. Okay, so in this case, okay, you can have for this, all these have ID. So they can have van der Waals forces. Okay, so the answer is going to be ionic. Two different elements. Yeah. ID can happen for polar or non-polar also. Okay. Now, I will continue, okay, with this. Whoever needs to leave, you can leave. Okay. So no, I'm not going to hold you over here. Yeah. So thank you, everyone. Okay. Okay. If you need to leave, you can leave. Okay. Now here, okay, plus x and plus y. Okay. This one I already taught you just now. Okay. So please take note how to do. Okay. But I can just go through this again. Yeah. So x, okay, you have helium. Okay, is going to be 5 dm cube, 12 kilopascal. Y is going to be 10 dm cube, okay, and 6 kilopascal. So just use PV equals to nRT. Okay, so I'm using the same unit over here. Okay, so I'm not converting the unit. So 12 times 5. So the N I'm using N1, so RT. Okay, then okay, this one is going to be PV equals to nRT also. So this one is going to be 6 times 10. I'm using N2RT. Now, after you mix them together, okay, you are going to have P1 contributed by this X. Yeah. P1, okay, the volume now is going to be 5 plus 10, so 15. Then still N1 RT. So here, okay, this is going to be P2. Okay, P2, the volume is going to be 15 when you add, okay, then it's going to be N2 RT. So what you need to do, you need to combine both of them together, okay, and you will get 60, okay, divided P1, 15 equals to 1. All these N1, R, and T will cancel. So P1, you will get 4 kilopascal. The same thing over here, okay, if you cancel is 60, P2, 15. Okay, you will get 1. So P2, you will also get 4 kilopascal. So if you add them together, we want P1 plus P2, which is going to be 4 plus 4, which is going to be 8 kilopascal. Okay, so that is going to be giving the answer for this 8. Now, which equation can apply to ideal gas? Okay, so this one, okay, still PV equals to nRT, okay, and you are introducing density over there, okay. What is density? Okay, density is going to be mass divided by volume. So you just put P, this is going to be nRT divided by V, okay. What is N? N is going to be mass divided by MR, and then RT divided by volume, you can just put 1 over V, okay, times 1 over V. And, okay, you can actually have, okay, M divided by V is going to be density. Okay, you can ask them to come in. You will get density. Okay, you will have density and you will have RT divided by M. Okay, so this is correct. Okay, this is correct. And then if you look at, okay, this one, okay, this is related to concentration. Okay, so when it comes to concentration, okay, you can see that, okay, PV equals to nRT. Okay, concentration is number of moles divided by volume. Yeah, so number of moles divided by volume. So you just use P equals to nRT divided by V. Number of moles divided by volume is going to be supposed to be concentration. So it's supposed to be this alone, not this. This is wrong. Okay. So this is automatically wrong. Let's look at this. Okay. PV must be always nRT. And when you include M over there, which is going to be the molar mass, okay? Molar mass cannot just simply come over there. It's supposed to be, okay, it's supposed to be mass divided by M, then RT. Suddenly where the M disappeared. Yeah. So this one also cannot be the answer. Okay. So therefore the answer is going to be only one is correct. Okay. So if you move further, okay, this one we have done. Okay. I will just go through very fast also. Okay. So before you open, okay, before you open, this is going to be V, this is 3V. Okay. So before you open, okay, PV equals to nRT. So the pressure was 1 times 10 to the power of 5. Volume is V, and Okay, 8.31. So if you want to maintain R also can. Okay, the temperature was 20. 20 plus 273 is going to be 293. Yeah. So after that, okay, you have another version which is going to be after you open. Okay, after you open, you are going to actually have the final pressure. So I just put P. Okay, the volume now is V plus 3V, total 4V. So I'll just put 4V equals to N. N is still the same. So R and the T now is going to be raised to 100. So 100 plus 273 is 373. Okay, so what we do is, okay, we just have this equation 1, equation 2, you divide. Okay, what you will have is, okay, let's say 1 times 10 to the power of 5 V divide with 4 PV equals to NR293 divide with NR373. You cancel this, cancel this, cancel this, cancel this, cancel this, cancel this, and find out what is P, and you will get the answer as 8. Okay. Now, a student borrowed a friend's chemistry notes and copied out the notes and so on. Which statement is correct? Okay, the less ideal, yeah. So something behave less ideal under what condition? Okay, less ideal. It means ideal means you must have lower pressure, higher temperature. Less ideal means should be at high pressure, less ideal. Okay, low temperature. Okay, less ideal. Yes, correct. Okay, and that can be easily liquefied. Can be easily liquefied means when they are compressed. Okay, gas is being compressed. It means that they are going to form a lot of attraction, okay, between each other. So if they can form a lot of attraction, it means less ideal. Yeah, we don't want any attraction. So this is going to be less, okay, so can be easily liquefied, which is going to be less ideal. So the answer is going to be 2 and 3. Okay, now, so copper and iodine. Copper must be all metallic bonding. Okay, iodine, okay, please remember, iodine, okay, they say between neighboring iodine molecules. So between I2 and I2. So it must be, okay, cannot be covalent bond. Yeah, must be van der Waals forces. It can be either, okay, ID, PD, or hydrogen bonding. Yeah. So this one is the old syllabus. They put van der Waals forces, but in future they might actually put just induced dipole, instantaneous dipole, induced dipole. Yeah. So this one will be D. Which features structure of bronze? Okay, so this one is going to be no longer in our syllabus. Yeah, so I just put it over there so that you can answer also. It's an alloy. Okay, so there is lattice of ions with C or delocalized electron. Yes. Okay, different size of atom unable to slide over. Yes, make it stronger. And it has ionic bond. No, no ionic bond. So the answer is going to be 1 and 2. Yeah. Which of the following has simple molecular lattice? Simple molecular lattice, yeah. Copper is giant metallic structure, yeah. And then calcium sulfide is going to be ionic. Any ionic, they will form giant ionic structure, yeah. And then phosphorus is always P4, so it's simple molecule. And then nanotube, no longer in your syllabus, but I told you nanotube and fullerene are simple molecular, yeah. Nanotube and Buckminster fullerene, simple. Okay, so this is going to be 3 and 4. Now, question number 30, the last one. Okay, for the ideal gas. Okay, this one I showed you in the on the whiteboard the other day. Yeah, so you can see the ideal gas must follow straight line, and you can see from the graph, okay, which one deviates the most. Okay, Z deviates most. Yeah, it will really give you a different value. So if Z is going to be deviating the most, it means it must have the most intermolecular forces of attraction. And you can see hydrogen, ammonia. Ammonia should be the answer because ammonia can have hydrogen bonding. Okay. And then the one that deviates the less is white. Okay. Must be the one that do not have a lot of intermolecular forces. So the one that do not have a lot of intermolecular forces is hydrogen. How do I know that? Because hydrogen, okay, and nitrogen, they are both ID. But hydrogen, okay, you see the size 1 plus 1, 2. Nitrogen is going to be 14 plus 14 is going to be 28. Nitrogen is bigger, more ID. So it's going to be the answer is going to be B. Yeah. So that's all from my side. Yeah. Okay.